All right, these are the notes for the second part of section 1.7. We're solving more inequalities today. The first lesson, 1.7.1, was dealing with solving linear inequalities. Now we're going to deal with some quadratics, also some higher level degree in inequalities, as well as we'll also talk about solving rational inequalities, which get a little complicated. Okay, so the first one, just a real simple example. This is a linear equation. So just to kind of remind us what we did in the first part, we would solve this for x. Notice I added 2 to both sides, and then I rewrote it so the x is by itself on the left. X is greater than 2. We'll use a parentheses. You might use an open circle as well, but I'll use a parentheses opening to the right and then an arrow going to the right. So that means that 2 is not inclusive of the answer. The answer does not include 2, but anything greater than 2. So we can also look at a similar situation here where we have instead, notice it's very similar to the first equation. 0 is less than x minus 2. Here we have y is less than x minus 2. If we included the y instead of the 0, then we're dealing with sort of 2 dimensions. So we're graphing a line, and so we can see we have the line here. And you can see how these two are related. If we concentrate on just the x-axis here in the middle of this xy coordinate plane, then really these solutions are almost are really identical. This answer doesn't include this point here at 2 because the line is dashed, so it's everything to the right of that. And just like everything to the right of 2 here on just when we were dealing with just one variable. This idea will be helpful when we look at the next couple of graphs. Okay, so here's a parabola, and you can see now we haven't really graphed parabolas. You might remember this from graphing parabolas in Algebra 1, but you can see here we have a parabola. In this case, it's an inequality, and so it's a dashed parabola instead of a solid parabola, just like you would deal with a line, but here we're dealing with a curve, and we've shaded below it, so it's everything below. And then the next one is greater than or equal to. So here we're going to have a solid parabola and we're shading above it. And the last one is greater than, so we're shading above it, but it's a dashed parabola. Also, this parabola opens up down because the leading coefficient, -2, tells us that it's going to open down. But if we think about looking at those equations 1, 2, and 3, and eliminate the y and only deal with the x variable, then, just like we saw in the last slide, then we can really just concentrate on just the x-axis. And so you can see that the x-axis for the first one would be everything but 2. The next one is going to be everything in between those 2 boundaries, and the third one, everything is going to be outside the 2 boundaries that we get. It happens to be where the parabola crosses the x-axis. All right, so let's kind of use that idea here. So first, let's solve this inequality. And so what we're going to do is let's factor it. Let's kind of pretend it's an equation for a moment and factor it, and that will give us 2 x values. Well, those are going to be our boundaries. That's where, if we were going to draw the parabola, where the parabola would cross through the x-axis. So if we were going to graph this relating parabola, you can see that the parabola would cross the x-axis at those 2 boundaries that we got from pretending it's an equation and factoring it. But what we want to concentrate on is just that x-axis, because we're not graphing that y is greater than or equal to. We're graphing 0 is greater than or equal to. So we only really need to concentrate on the x-axis or this, we can tell from the graph that it was between these two. All right, so, but this is a lot of work to graph, so we're not going to actually do it this way. So this is an interval notation. It's from -1 to 6 inclusive is our answer, but we're not going to use this approach. The next slide is going to show us how we're really going to graph, how we're really going to find our solutions without graphing. All right, so here is, I guess, is that same solution, same equation that we just did, I think. Anyway, so what we're going to do without graphing is we're going to take this equation and we're going to pretend that it's an equation, and then we'll solve that equation, and by solving that, we found the two boundaries. Okay, so we are got the two little dots right there at -7 and at 1. All right, so now what we have to do is those two solutions, or those two boundaries, break our x-axis up into 3 regions. And we have to figure out, do the values in region 1 satisfy our inequality? Do the x values in region 2 satisfy it? Or do the x values in region 3 satisfy it? All right, so we're going to test a number from each region. All right, so I'm picking -9 in the region 1, 0 in region 2, and 4 in region 3. So you're going to pick, whole numbers, obviously, but you just want to pick a value that's easy, like 0 is a pretty easy number to plug in. All right, and so what we really want to do is we want to use our factored form, take it back, put back the inequality, and use factored form. So if we put a -9 in for x, and again, in factored form, we want to be able to compare it to 0 pretty quickly. And I don't care what that -9 plus 7 is -2. All I care about is that it's negative, because the product of these two things is going to be compared to 0. And is it positive or negative? And it's going to be able to tell me whether or not it satisfies this inequality. So a -9 into the first binomial gives me a negative. -9 into the second binomial gives me a negative. A negative times a negative is a positive. And is that positive number greater than or equal to 0? And that would be true. And so I know that first region, anything to the left of -7, is part of my solution. All right, now let's check our next value, 0. So plugging a 0 in, I get a positive for my first binomial and a negative for my second. So that's going to be a negative product, and that is not greater than 0, and negative would be less than 0. So that would be false. That region is not. I don't need to check more than one value in the region. By checking one value, that one value is false, I know all the values are going to be false. All right, and then the last one. X equals 4 is plugged in, and I get a positive times a positive, and that is a positive, and that is indeed greater than 0. So that satisfies. All right, so how do we write our answer, and how would we graph? How do we graph our answer? And so you can see that it's going to be, now we are going to use more, nowadays I'm using, rectangular brackets or parentheses. Here I'm using the closed circle, which is fine. You can still use a closed circle. So it's -infinity up to and including -7, or starting at +1, inclusive of +1 up to infinity. All right, let's try another example. Here on letter B, x squared plus x is greater than 6. So we want to set it equal to 0, bring the 6 over, but then also, again, just kind of set it equal to 0 so that we can factor it and find our boundaries. So our two boundaries are going to be -3 and 2, and we want to test it in factored form. So we want to test the binomial x plus 3 times the binomial x minus 2 is greater than or equal to 0. So we'll pick the different values in different regions. So in the left region, any value I put in there is going to make the first binomial negative, and the second one binomial is also going to be negative. Negative times a negative is a positive, So that satisfies the inequality. The positive result will be greater than 0. Therefore, that one's good. The second one, the first binomial will be positive for anything bigger than -3. And to the left of 2 is going to give me a negative for that second binomial. So I have a positive times a negative, and that is a negative, and that is not greater than 0. And the last region, both binomials will be positive. Positive times a positive is a positive, and that's greater than or equal to 0. So we're good. So the outer regions work in that case. So we have negative infinity up to and including -2, or including -2 up to positive infinity as our solution. Okay, let's try another one. So number C, letter C. Again, we want to pretend it's an equation and factor it. And that gives us our two boundaries. So we have 9 halves and -5 halves. And so the equation that we're going to test again, we want to do it in the factored form so that it's easier to check individual values. We don't care what the value result is. We just care if it's positive or negative. So that first region on the left, when we plug a value out there, we get the first binomial and second binomial, both negatives. Negative times a negative is a positive, so that is not less than 0. So as a result, that would fail. The region in the middle will give us a negative times a positive, which is a negative, which is less than 0. So that region is going to be good. And then the last region gives us a positive times a positive, and as a result, the product will be positive, and that will fail. So our region is in between, so it's non-inclusive of -5 halves up to, but not including 9 halves. And so that is our solution. All right, so here's an example of a problem dealing with projectile motion and an inequality, so kind of a word problem. If an object is launched from the ground level with an initial velocity of 144 feet per second, then when will the object's height be greater than 128 feet above the ground? So here's an inequality, right? We want to know when will its height be higher. So this is a range of values. All right, so if you remember, the equation for the height is just the general one is given here. And then we have the initial height, they said, from ground level, so that's 0. S sub 0 is 0. V sub 0, the initial velocity, 144 feet per second. All right, and now we just want to know when the height is greater than 128, so we want to put a less than sign in there, right? We want the right side, which is our height, to be greater than 128. Okay, so we can set that equal to, like, bring the 128 over, and then we want to sort of factor that if we can. Well, first, I'm going to divide through by -16. Remember, I have to change the direction of my inequality. And then hopefully that would factor, and it does. T minus 1 and T minus 8. And so that tells us our boundaries are going to be at 1 and 8. So that tells us that the projectile is exactly 128 feet above the ground at 1 second and at 8 seconds. So in between those, it's going to be higher up. All right, but we can certainly test that region, test these, but it'll be negative and negative, which is a positive, and then a positive and a negative, and then remember, it sounds backwards, but remember, we multiplied through by a -16. So now we're looking for things that are less than 0 rather than greater than 0. So it's between those two things there. Okay, so well, it does say greater than 128 feet, so that's why we're not including the 1 and the 8. So exclusive of 1 and 8. All right, now you don't have notes, I don't think your notes include these examples, but I just wanted to go through a couple more like special cases. We're not going to see these too often, but I just wanted to run through these really quick. So this is a perfect square trinomial. And so what happens when you get a perfect square trinomial? You really only have one boundary, and it's repeated. All right, so we call this a multiplicity of two. So notice as we went through the boundaries before, the whether the values in that region satisfied the inequality, it sort of flip-flopped, right? So it was success, failure, success as we went through the boundaries. But when you have a multiplicity of two, you'll notice that, first of all, you only have one boundary because it's a repeated root. And when we test both sides, you see that they either both work or they both don't work. So in this case, a value to the left would be a negative when we plugged it in, but that negative is being squared, so it's going to be positive. And on the right side, it's going to be positive, and then when we square that, that's also going to be positive. So the solution is everything except 4. So all real numbers except x just cannot equal 4. So we have in this case, I did an open circle there. Okay. And so you could also write it as negative infinity up to, but not including 4, or exclusive of 4 up to infinity. All right, so that's kind of a special case. You can think of it as sort of a parabola, a perfect square trinomial. If you were to graph it in an xy coordinate plane, the parabola just touches the x-axis at its vertex. So there aren't two points, two boundaries, because the parabola doesn't cross the x-axis at two spots. In this case, only one value, one repeated root. All right, and then this other one, this is an example of a cubic. So, I would say let's factor this. Let's solve this using factoring. So again, I pretend it's equal to 0. I factor an x out, and then the resulting trinomial is factorable. And so I have 3 boundaries this time, 3 possible solutions if this was an equation. So I have 3. And then I want to test. Now I have to test 4 regions. So I want to leave it in factored form. And I kind of put them in order. You notice the first binomial, x plus 4, gave us the boundary of -4. The value in the middle, x, that gives us a boundary of 0. And then the x minus 5 gave us the boundary of 5. So sometimes it's helpful if you put your binomials in the order that they show up on the number line, right, based on their boundaries that resulted from them. And you can see that in this case, we have the first region is negative times negative times negative, which is a negative, which does not satisfy the greater than 0. And so as we go through these boundaries, notice they flip-flop. None of these boundaries are from a binomial of multiplicity 2. They're all multiplicity of 1. So as I go through each boundary, technically I really only need to check one boundary, and then they will flip-flop as they go across. So it doesn't work, it does work, it doesn't work, it does work. Okay? And again, be careful, that's not true if one of those boundaries had a multiplicity of 2, then they're the same as you go across. They don't flip-flop. All right, and then this graph I just here showed kind of, this is a cubic that we would be shading below, and you can kind of see why then, we're not really graphing the whole XY coordinate plane thing. We're only doing the x-axis, but just to help you visualize why this graph results in one like it does. All right, so the last part of today's lesson really is about solving rational inequalities. And so let's start by doing this problem wrong. So if I give you this problem, most people would probably say, oh, let's treat it as a proportion almost, and we'll like cross multiply. We'll multiply both sides essentially by x. And so I get x minus 1 is greater than or equal to 2x. And then I would probably add or subtract an x from both sides. And then let's rewrite it so that the x is on the left. So x is less than or equal to -1. And then we want to check, like, let's check this answer. So let's take a value that is less than -1. So I'm picking -2, and I'm plugging it into the original equation. So like plug it into this thing to check it. And so when I do plug -2 in, I end up getting, with, well, -3 over -2, which is 3 over 2. And then that should be greater than 2, and it's not. 3 halves is not greater than 2. So something's going on here. Like this solution does not work. So what's going on? And so the issue is, if you think about it, when we multiply by a negative value, we have to change the direction of the inequality. And we multiplied both sides by x, which is a variable. So that's causing problems. Like, so we can't multiply both sides of an inequality by a variable, because that just messes things up. Also, the original problem has a domain issue at 0. And by multiplying by x, we kind of get rid of that. That causes a problem as well. So what do we have to do? Well, what we do is we set this thing, sort of set it equal to 0. So we subtract 2 from both sides. So it's not really setting it equal to 0, but you know, we subtract 2 from both sides. Like when we were solving quadratics, we set it equal to 0, right? And then try to factor or something. But in this case, what we want to do is get a common denominator. So I'm going to multiply that -2 by x over x. And so I get 2x over x. And now I want to just combine those two fractions. And so combining like terms then gives me -x minus 1 over x is greater than 0. All right, so now what we want to ask ourselves is, now that we have this thing simplified on the left-hand side, it's greater than or equal to 0, we want to ask ourselves, well, when is -x minus 1 over x, when is that greater than or equal to 0? So if we took that graph, we could graph that function and sort of say, okay, so when are the points on this graph? When are those points at a y location above 0, right? Because we're thinking of f of x or y. When is the y value greater than 0? And so you can kind of see anytime it's above the x-axis, that function is going to have a value greater than 0. All right, so we can kind of just look at the function and see when is it greater than 0 or equal to 0, and we can see from -1 up to 0. Okay, now notice this function is kind of strange, right? So it has what we call an asymptote. We haven't really graphed rational functions yet, so you may not be familiar with this term, but this function has a domain issue at 0, right? X cannot take on a value of 0. We know that from the original function, the original inequality, because if an x value of 0 would make our denominator 0. And so funny things happen close to that. And so this is why we have a vertical asymptote at 0. The function gets closer and closer to it. As x gets closer and closer to 0, the y value explodes and goes off to infinity. Also notice that if we jump across that asymptote and now we're on the positive side, the y values of the points jump. So they're up at positive infinity, and then on the other side of that asymptote, they're down at negative infinity. So the sign has changed there, right? Okay, so that's kind of important. So again, we're not going to really graph this thing. So we want to be able to figure out where should we be looking for sign changes. And so if we look at the graph, where does the graph cross the x-axis? The y values change from positive to negative when the graph crosses the x-axis. So you can see that clearly it's at an x value of -1 the y values change from positive to negative. And so we want to look at really when do the sign of our function change? When does the sign from positive to negative or negative to positive? When is it changing? And it changes at the x value. So we don't want to graph this thing. Instead, we're going to look at where is the numerator equal to 0. So set the numerator equal to 0 and then solve that. And that tells us the x value that will make our numerator 0. All right, so the x value of -1 causes the function to have a value of 0. And then what happens, that means that the function's crossing the x-axis at that point. So that means on one side it's positive, on the other side it's going to be negative because it's crossing through the x-axis. Okay, now we can see here clearly, because it's graphed, that on the left side of -1 that has negative, the function is negative, and on the right side it's positive. But again, we're not going to be using a graph, so we're going to have to test regions. All right, and so it's the where the numerator is 0, but also where the denominator is 0, because where the denominator is equal to 0, we're going to end up with some kind of domain issue, and so as a result, we'll have an asymptote there. So we have two boundaries. One is going to be at -1, and one is going to be at 0. And so now we just have to test our regions. So we want, when we test our regions, we really want to test using this function, not the original equation, but the one that is set equal to 0. And so we want to plug in a value out there. I'm plugging in -3. And again, I don't care what the top value is and what the bottom value is. I just care about the sign because we're comparing it to 0. So we have a positive on top divided by a negative. That's a negative. And that does not satisfy this inequality of greater than or equal to 0. So that part would fail. The middle part, when we plug that in, we'll get a negative over a negative. And then in the third part, we get a negative over a positive. And so that fails as well, because a negative divided by a positive is a negative, and we want the quotient to be greater than 0. So the only region that works is that part in the middle. And so we saw that in the previous thing when we were just looking at the XY graph. But again, we're not going to be looking at that graph, right? We're not going to graph this pretending it's a function. It's an inequality. So we're not going to graph it. Instead, we're going to test the regions on the numbered line. Okay, so our answer, again, like we saw when we looked at the graph of the function, it was -1 to 0. All right, let's try another example. All right, so B here, solve this inequality. So again, we're just going to bring the 4 over. And then we have to get a common denominator. So I'm going to multiply that 4 by x minus 3 over x minus 3. So we have a common denominator. Now let's write it as one fraction. And also notice that I took this -4 and I moved it up to the 4. That way I remember to distribute the negative when I take it in to that binomial. And as a result, I made it a plus out in front here. So I turn this into a plus, and I move the negative up to the 4. Remember to do that. That's pretty crucial. That way you remember, because if invariably, a lot of times students leave this as a -12 out. You know, this makes it, they make it a -12 instead of the +12 that it is. All right, and so then let's just continue simplifying. And so I end up with -4x plus 18 over the quantity of x minus 3. So we need to, again, figure out where the numerator is equal to 0. So set the numerator equal to 0, solve that, and do the same thing for the denominator. And so that gives us my two boundaries. I have a boundary at 3, and I have a boundary at 9/2. Now I just need to test those regions. And again, what am I using to test? I'm using this form of the equation to test this, okay? So I end up with a positive over a negative, and that's a negative, which is less than 0. So that is satisfies our inequality. The middle region, we get a positive over a positive when I pick a value, and that is a positive, which is not less than 0. And the last one is going to be a negative over a positive, and that one is going to be a negative, so that would be less than 0. All right, so our solution graphed on the number line is everything from negative infinity up to, but not including 3, or everything from 9 halves, exclusive, of course, of 9 halves, up to infinity. All right, now this one is sort of already sort of solved for us, but ultimately we want to set the numerator and the denominator equal to 0. So factoring that denominator will be helpful, finding to find where it's equal to 0. And so remember, this one has a multiplicity of 3. I'm saying the 3 boundary came from a binomial with multiplicity of 2. So be careful, it works the same way that we saw when we were doing quadratics. So we have a boundary at -4 and a boundary at 3. I just know that as I go across that boundary at 3, it's not going to flip-flop like it does often with other boundaries. So let's test our regions. All right, so again, we're sort of using this version of the inequality to test, and we get a negative over a negative times a negative, which will be a positive. So it's a negative divided by a positive, which is less than 0. We are hoping that it would be greater than or equal to 0. That's the inequality that we have. The next region is going to be a positive over a positive. Essentially, the denominator is always going to be positive here because it's a binomial squared. And then the last region, of course, it does not flip-flop. It's still going to be a positive over a positive. Okay, now let's talk about when the boundaries are inclusive versus exclusive. The denominator can never be 0, right? That would be a domain error, right? So we can't have the denominator ever be 0. So we can't ever include 3 as part of our solution. So I know 3 is not going to ever be part of my solution because it came from a denominator. So we're talking about open circles or parentheses when we're talking about 3. Now, -4, that comes from the numerator. And in this case, having a -4 as an x value is okay, and this actually satisfies our inequality because then we have a 0 on top, and the inequality is greater than or equal to 0. So the equal 0 is good here. So we're going to have a square bracket at 4, but parentheses at 3. And again, that's because that 3 came from our denominator. We can never have a 3 in our denominator because it would give us a 0. But we can have a -4 in the numerator because having a 0 in the numerator actually satisfies the inequality this time. Okay, so we have inclusive of -4 up to 3, but not including 3. And then from 3, but not including 3, up to infinity is our solution. Okay, so this is the homework for this last part of section 1.7.